You'll be delighted to know that the derivative of e to the x is e to the x. That is, the derivative of e to the x is e to the x. It seems like a remarkable situation, and it certainly is. This is such an unusual curve. Now, let me show you what this means graphically. It's a situation where, let's see, here's the graph. Now, here's 1, and the graph goes through and rises rather sharply. But along this x-axis, if we take a value of x, and let's say that it's 2. Let's say that we use 2. And then we go up, and at that point on the graph, we locate the spot, and then we measure the slope of the tangent line. You know, that's what derivative is all about. The slope of the tangent line at that point is e squared. You see, it's the idea, the derivative of e to the x. When x equals 2 is e squared. So the slope of the tangent line is e squared. You see, so that's that slope. Now, if we introduce a situation where the exponent is no longer x, but it is an expression involving x, then we have the notation is e to the u. And the derivative turns out to be e to the u times the derivative of u with respect to x. And a nice notation for that, I think, is this, e to the u times u prime. I kind of favor this notation over this one. It's just a little easier for me to use, but you take your choice. Now, here's an example. We have f of x is e to the 2x minus 1. So the derivative of the function is e to the 2x minus 1 times the derivative of the 2x minus 1. The derivative of this expression is 2. So we have 2e to the 2x minus 1. Here's another one. Y is e to the negative 3 over x. Now, when you're faced with problems like this, what you might do is just resort to our definitions. And you might begin like this. You might say, well, okay, this is of the form e to the u. And I know that the derivative is e to the u times u prime. Now, let's identify the parts of this. Well, the u is the negative 3 over x. So you might drift over to the side and say, u, for my purposes here, is negative 3 over x. And now let me write this in a form where I can take its derivative rather easily. I'm going to kick the x up into the numerator and write it as x to the negative 1 power. And now it's pretty easy to find u prime. U prime is, well, negative 1 times negative 3 is 3, and then x to a power 1 less than that is negative 2. And now I can pop this back into the denominator. You see, so 3 over x squared is what u prime is. Now let's pull back over here. So e to the u from right up here is e to the negative 3 over x, and then the u prime part comes from over here, 3 over x squared. Now all we need to do is clean it up. Now, there are a lot of ways of writing this correctly. One way would be to leave this e to the negative 3 over x in the numerator with the 3 as its coefficient. Another way would be, since we have a negative exponent here, is just to kick this factor down. It really depends. You know, leaving it in a particular form a lot of times depends upon how you're going to use the information as an extension of the problem. Usually we're doing this kind of, we're performing this kind of function in order to achieve something else. But right here, this is fine. Here's one that looks a little more complicated. It's a big fraction here. Notice we have a binomial in the numerator of the fraction. And part of the strategy here, part of being able to do this effectively, is to put it into a condition where we can take the derivative rather easily. So we sort of distribute this 2 as a divisor among the two parts of the numerator. And so we would write separate fractions. And gee, we'd like to see distinct coefficients here. So I can write this as 1/2 e to the x. And over here, minus 1/2 e to the negative x. And now I'm ready to go. I have 1/2 e to the x times the derivative of the x. Oh, that's just 1. So I don't need to put anything down here. On this one, however, I have minus 1/2 e to the negative x, which is what I have here. And now I want to multiply by the derivative of negative x. Oh, that's negative 1. So the negative 1 times this negative makes this positive, and here's our our answer. I can put it back into a fractional form if I want to, e to the x plus e to the negative x all over 2. Gee, that's remarkably similar to what we started with, but maybe that's not such a surprise since the derivative of e to the x is e to the x. Here's a situation that uses this idea. And it seems so, I love problems that seem so complicated, and yet they really turn out to be rather simple. Let's pretend that these are telephone poles. And the wire that's stretched between them has a certain sag in it. And the graph, this curve here, is called a catenary. And the catenary here can be modeled by this equation. We're assuming here that the two telephone poles are 60 feet apart. So 60 feet apart. Let's say that we'd like to verify that the lowest point in this sagging wire is right in the middle between the two telephone poles, and let's try to figure out how far the wire sags from the telephone poles down to the lowest point. Well, let's see. Now, in this model, you notice that the domain is that x is between negative 30 and 30. X is between negative 30 and 30. That seems to imply that if we're talking about a model for just this part of the curve, of all of the wires, that we are positioning our x right in between this 60. That is, our coordinate plane is situated like this. You see, it's kind of like this. Here's our origin right here. So we are, our domain is an x from negative 30 to 30 for a total distance of 60 feet. All right, so that's the idea. Now, in order for us to find a minimum spot on that curve, we're going to need to take derivative. So let's set ourselves up for that. Now, there are a number of ways of doing this. One way is to multiply the 30 times each part, and I'm kind of doing that so we can separate our thinking among the two different terms here. But really, it's not necessary. It's done a little bit differently in your textbook, and you might have a look at that. But to take the derivative, let's see, y prime then for this term would be the same term times the derivative of this exponent. Now, this x over 60 can be thought of as 1 over 60 times x. So the derivative here is 1 over 60. So we have this. Now let me carry this one step further. The other part is going to be very similar, but while we have our mind on this, the 60 here and the 30 here cancel. 30 into 31, 30 into 62. So this is 1/2, you see, times e to the x over 60, and that's what we have right here. All right, on the other part, the derivative of this is this term times the derivative of that exponent. And remember, this is negative 1/60th times x, so the derivative is negative over, negative 1 over 60. And again, we have this 30-60 cancellation, so we've got minus 1/2 e to the negative x over 60. Well, what are we going to do with this? We have a derivative function now. Well, the critical points, critical values are at the zeros or undefined values involved here. There aren't any undefined values, but we need to find the zeros here. So we set this expression equal to 0. Let's do that up here. So we set 0 equal to the expression we're talking about, and we want to solve for x. Well, let's see. We'll separate the two terms. I'm just kicking this, adding that on both sides, and I get this. And now I'm going to use a technique that we haven't really talked about before. We haven't talked about solving exponential equations. Exponential equations are equations in which the variable that we're looking for lies in an exponent. And we'll talk about techniques for dealing with that situation a little bit later. But for now, doesn't it make sense that if e to this exponent has the same value as e to that exponent, you see, we have the same bases but different exponents, but these are equal to one another and the bases are alike, doesn't it make sense that these exponents have to be the same? You see, go like this. Sure, that makes sense. So if these have to be the same exponents in order to make this equal, then we can just set the exponents equal to one another. So negative x over 60 is equal to x over 60. Multiply on both sides by 60 and we find negative x is equal to x. And if we add x on both sides, we have this, and this is 2x equals 0. Divide on both sides by 2 and we find x equals 0. That's a critical value. That's exactly what we expected. We kind of expected that the lowest point in that sagging wire is going to be right in between the two posts. Doesn't that make sense? And now let's see how high the wire is from the ground at that point. And let's see how high the wire is at the telephone poles. Okay, so here's our equation, the equation that we started with. And if x equals 0, here's what happens. This x is 0. This is 0 over 60. This is also 0 over 60. Gee, e to the 0 power is 1. This is also 1. 1 and 1, 2. 2 times 30, 60. So when x is 0, y is 60. Now that means that y, that vertical distance, is 60 feet at the very middle of that curve. You see, at the middle of the dip. So the wire is 60 feet off the ground at that point. Now let's see how far off the ground the wires are as they are attached to the telephone poles. So we would let x equal either 30 or negative 30. You see, that's how far from the middle of the graph we are for the telephone poles. So if x is replaced with 30, then the x's are replaced with 30 up here, and we have this. Now, 30 over 60 is 1/2, so this is e to the 1/2 power, or the square root of e. And this is e to the negative 1/2, or 1 over e to the 1/2, or 1 over the square root of e. And now we need to use the calculator to make the calculation, and we find y to be 67.7 feet. And the difference between these two, the difference between 60 and 67.7, is the amount of sag in the wire. And the amount of sag then is 7.7 feet. Let me say something about this. If you're calculating this on the calculator, E can come up on the calculator. It comes up on the calculator as the second function on ln. And so as you're entering this, you would enter square root, and then for the E part, it's second function on ln. But what usually happens with calculators when you enter E, when E comes up, sometimes there's an automatic prompt for the exponent on E. Now if you just want E and no exponent, then enter a 1 for the exponent. So e to the 1 is E, you see. And by the way, you can just see E on the calculator if you want to by going second function ln and then enter a 1 for the exponent, close the parenthesis, hit enter, and it'll give you the value of E that we looked at before. But for this, just be very careful in the way that you enter things, because you need to close all of your open parentheses in order for it to come out right. But take a shot at it yourself. At any rate, the wire is sagging 7.7 feet.